Tired of walking up the stairs, an engineering student designs an ingenious device for reaching his third-floor dorm room. A 100-kilogram block is attached to a rope that passes over a pulley. The student holds the other end of the rope. When the block is released, the student is pulled up to his dorm room 8 meters off the ground. He is traveling at 2.2 meters per second when he reaches his room. So, we saw a problem which was similar to this in the dynamic section, but in this section we're going to use conservation laws to solve the problem. So, we have to start off doing the free body diagram. So, I have the force of gravity for the student acting downwards. That is equal to the mass of the student, which we are not given. So, we're just going to call that ms times g. Then I have the tension in the rope, which is going upwards. So that's T. For the block, I have tension going upwards. I have the force of gravity going downwards. Force of gravity for the block is equal to the mass of the block, which is 100 times 9.8, so that's 980 newtons. Okay, after I've done the free body diagram, I can fill out the motion information table. I have to do the student and the block. This bar graph is for the student, this bar graph is for the block. Event 1 is when the student leaves the ground. Event 2 is when the room is reached. And the next step is to fill out the motion information table using the definitions. So kinetic energy is equal to 1/2 mv squared. Gravitational potential energy is equal to mgh. And work other is equal to the sum of the magnitude of the forces other than gravity times the magnitude of the displacement times the cosine of the angle between the two. So, the block is released, the student is pulled up to the dorm room. When the block is released, the student and the block are both at rest. So this is 0 here and 0 here for initial kinetic energy. We are told that the student is traveling at 2.2 meters per second when he reaches the room. So, using the definition for kinetic energy, for the student, we have 1/2 times the mass of the student times 2.2 squared. We can't really do much with that because we don't know what the mass of the student is, but we can say 2.2 squared is 4.84. Divided by 2 is 2.42. I don't have a whole lot of room here, unfortunately, so I'm just going to kind of squeeze this in. This is 2.42 times the mass of the student, if you want to simplify that. Okay, then for gravitational potential energy, we have to choose where the height is equal to 0. So let's say the height is equal to 0 at ground level. So the initial gravitational potential energy for the student is 0. When the student reaches the dorm room, that's 8 meters off the ground. So this is the mass of the student times 9.8 times 8 meters. So that's the mass of the student times 78.4. Okay, and then for the work, this is work done by forces other than gravity. We're looking at the student here. Tension is upward. The student is moving upward. So the student's displacement is upward. That's in the same direction as the tension. So for the cosine of the angle between the two, since they're pointing in the same direction, tension's doing positive work. So cosine of the angle is 1. So the only force other than gravity I have is T. This is T times the displacement. The displacement is 8. Okay, so now I'm finished with the table for the student. Next, I look at the table for the block. The block starts at rest. When the student reaches the dorm room, the block is moving downwards, but because for kinetic energy we use the velocity squared, it doesn't matter that the block is moving downwards. So this is 1/2 times the mass of the block times the velocity squared. That is 242, and the units are kilograms times meters squared per second squared, which is equal to a joule. So this is 242 joules. When the student reaches the dorm room, now the block is on the ground, so the final gravitational potential energy for the block is 0 because it ends on the ground. The initial gravitational potential energy is m, which is 100, times 9.8 times 8, because it's starting at the dorm room 8 meters above the ground. That is 7,840 joules. Okay, remember that I want you to use the definitions to fill out the table, but if you don't have enough room to put everything in your table and you want to do some work down below, you can, but put the 7,840 in the table and the 242 in the table also. Okay, now for work, the block is moving downward, so the displacement for the block is down. This is the opposite direction of the tension, so the force other than gravity, tension, and the displacement are pointing in opposite direction, so this is the cosine of 180, which is negative, so this is minus from the cosine. T for the sum of the forces other than gravity, there's only one force other than gravity, times the magnitude of the displacement, so that's A. Okay, because this is the magnitude of the force and the magnitude of the displacement, the direction doesn't matter. The sign is just coming from the cosine of the angle between the two. Okay, so now we filled out the table. I guess next maybe we can do the bar graphs. So for the student, initial kinetic energy is 0, initial gravitational potential energy is 0, so that looks like this. Tension times 8, that's going to be positive. And let's just make that 2 blocks. Okay, and then I have positive kinetic energy and positive gravitational potential energy. Probably the kinetic energy is not equal to the gravitational potential energy, but I'll just say 1 block for each because I don't know how they compare. Okay, and then for the block, we have kinetic energy is 0. Gravitational potential energy is positive. Again, let's just make it 1 block, but it's probably not the same as the kinetic energy and the gravitational potential energy that we have there, so it is not to scale. The work is negative. This work is T times 8. This work is negative T times 8, so if this was positive 2 blocks, this would be negative 2 blocks. Okay, but you don't have to do it to scale. We're just trying to get an idea of what is going on here. Kinetic energy here is positive. Remember that KE1 plus GE1 plus work 1, 2 is equal to KE2 plus GE2. And KE1 plus GE1 plus work 1, 2 is equal to KE2 plus GE2. So we had 0 plus 0 plus 2 is equal to 1 plus 1, so that works. And now I have 0 plus 1 minus 2, that would be equal to minus 1, but the kinetic energy is supposed to be positive here. So I'm going to make that 1 block again. But in order for this to work, now I'm going to have to make this larger. So if it's something plus negative 2 is equal to 1, that's going to have to be 3 blocks. Okay, and I want, remember, this to be equal to this because we can see that from the table. But for the other values, I'm just guessing. Okay, so we've done the bar graphs, and Well, I can actually see from looking at here, this kinetic energy is 242. This is a lot greater than 242, so that makes sense with the bar graphs here. Okay, so the next step would be to use the relationship, which if you put the signs in for the bar graph, you can see the work energy relationship just by looking at the bar graph. So this is KE1 plus GE1 plus work 1, 2, and let's just put other in there to remind ourselves that this is the work done by the forces other than gravity because we included gravitational potential energy. This is equal to KE2 plus GE2. Okay, I have to do this for the student and also for the block. For each one, I just look at what I have in my table here. So KE1 is 0, plus GE1 is 0, plus T times 8 is equal to KE2, which we said when we simplify it, we get 2.42 times the mass of the student, plus GE2, which is 78.4 times the mass of the student. I have two unknowns in this equation, so the only thing I can do to simplify this is pull out the mass of the student. So 2.42 plus 78.4, that gives me 80.82, so it's the mass of the student times 80.82. Let's call this equation 1. Okay, so now I have one equation with two unknowns. So now I have to look at the block before I can do anything else. I'm going to use the same equation here. So the work energy relationship says KE1, which is 0, plus GE1, which is 7,840, plus work 1, 2, this is the work done by forces other than gravity, is negative T times 8. That's equal to KE2, which is 242, plus GE2, which is 0. Well, now this is nice. I have one equation, one unknown, so I can solve it for the tension. So let's bring the T times 8 over to the other side and the 242 over to the left-hand side. So we have 7,840 minus 242 is equal to T times 8. Therefore, T is equal to 7,840 minus 242 divided by 8. That gives me for tension 949.8. Or I can round to 950 newtons. In this problem, they do not ask me do they ask me? No, they don't ask me a specific question. Okay, so I would want to, after filling out my table, look at what the unknowns are. That would be the tension and the mass of the student. So it's sort of similar to what we did in the dynamics section. You do your free body diagram. You can find all the forces and the unknown masses. Or you could do this. Use the definitions to fill out your table, and after doing that, find all the unknowns. So we're going to have to find tension and the mass of the student. I'm going to put the 950 up here. So that I know that I found it. And then I'm going to look for the mass of the student. So now, using equation 1, I have T times 8. Let's go back and use the 949.8 for the tension. So this is 949.8 times 8 is equal to the mass of the student times 80.82. Therefore, the mass of the student is 949.8 times 8 divided by 80.82. And that gives me 94.016. Let's just round that to 94, and that mass is in kilograms. Let's box what we have here. This is the mass of the student. So we found the unknown mass, we found the unknown force, we did the bar graphs. Remember, the bar graphs don't have to be to scale, but this plus this plus this should equal this plus this. We did the free body diagram, and that concludes problem 137.